Cool. So I figured that it would be best to like get a little bit of direction from you as to what would be coolest to see, because I have a lot of stuff that I can talk about for a while, a long time. So I can go from like a pretty basic intro, but I could also do like a more specific deep dive into the tech of like how different things work, or I could just focus on more top end use cases. Or yeah, like what are some of the things that people are interested in hearing about?
So you hear me okay?
It's a little bit breaking up. If you type it, then that would be awesome.
Can you hear me now okay?
Yes, I can hear you fine.
Okay, so just some of the very basic things. You know how to IPFS add a file into the system, okay? But just a couple of things I got stuck on. Easy to add a folder with a number of files inside it, grand. It's when you want to add a next file number 6 into the same folder, like I'm used to using on a Windows Explorer machine, for example. That kind of thing. How do you manage when you change the contents of a file, but we want to keep the same URL to the users that are out there? And then also, how do you digitally sign a file? And that's around, say, managing basic CSV files. And the other thread, I don't know how far it's developed with yourself yet, about linked data. When we spoke to you before, you had good ideas on JSON or stuff like that. So maybe you could share with us where that direction is going. And then finally, I think it's very useful. It could be application QR reader, you know, like the sample quick code reader that you have. Like, I was surprised that you can have applications so easy on IPFS as well. So it'd be nice to see. So those 3 areas: handle files the same as Windows Explorer, the linked data, and then the applications. That's what I'd be interested in, please. If you can show us that, it'd be great.
Sounds good. Other people?
Maybe a bit of an overview what IPFS actually is as well.
Sorry, it broke up a little bit. Could you repeat the last part?
A little bit of an overview of what IPFS is. People here who have never heard about it.
Yep, that sounds good.
As well, so I don't really know what IPFS is, and I'm just wondering what are some of the use cases in the real world.
Mm-hmm. Yep, sounds good.
And how to yes, to create permanent data store and data. I think it's overlapping with what Adrian was asking.
Yep. Cool.
Yeah.
Sounds good.
Yes, that's.
All right, awesome. So I think like one of the cool things about data as well is that I actually started working on IPFS because I wanted to build I wanted to fix some problems with data. Like I think there's a whole bunch of issues with how we do data management today. And this is kind of where IPFS came out of. So I thought it'd be cool to like just talk a little bit about that first, and then jump into kind of like a high-level overview of like what IPFS is for the people that don't know it yet, and then just go straight into like the use cases, I guess. And then I have a bunch of ways in which I can like dive into explaining different parts of the tech, like how like the linking actually works, and how does the resolution actually work, and how is content discovered, or how does the signing work, and all that kind of stuff. So we can cover of those whichever makes sense, but we can like jump around to that stuff. So cool. I'll try to like just blaze through the stuff that I had before on like open data. So here I'll share again. Let's see. Ooh. Definitely like presenting through Hangouts is not as good as it ought to be or could be. Cool. So all right, we're back here again. So yeah, so back a while back, I was working on. So this will go back for a while. So this was a presentation that I made in 2014 for a tool that I was making called Data, and a package manager that I was making for Data called Data DEX. And so the idea there was that data management has a whole bunch of problems that software engineering solved. And I'm just gonna kind of go through these slides really quickly. I'm sure that you know a lot of these problems. So the kind of problems that I identified were there's a bunch of issues in distribution. Like, it's very inefficient to move around data. Like, if you have data sets that are hundreds of gigabytes or terabytes or petabytes in size, it's very inefficient to move them around the internet because the way that the network is set up, you may not have the fastest pipes to wherever it is that you have to route the data through. And many times you want the data to move from one computer to another, sometimes in the same room, sometimes in the same building. And you really shouldn't be moving it through the backbone. And many times as well, there is usually just one host for the data, so through HTTP or FTP or something like that. And in reality, you should be using the bandwidth of everybody else, like being able to collaboratively share the bandwidth. Another issue is versioning. So I'm sure that people have seen horrible versioning schemes with how people use data. I think you guys use CCAN at some point, right? So that's already really good, and you actually track the versions and you track the different things. But most people that use data and most people that generate data sets and so on don't do that at all. They don't version. Oftentimes, certain data sets are no longer available. Certain versions have disappeared from the internet. You can't even get them back. And many times there are papers that reference data sets that are no longer available, so the results cannot be reproduced anymore. So this is a serious problem. So yeah, there's this whole notion of permanence that is kind of broken with how people are using data in the internet. They don't ensure that the data stays there over long periods of time. And this is I'll go in a bit more into why this happens. Then there's another issue of indexing. How do you find the data sets that you're looking for? How do you find data by specific people and so on? There's many different repositories. They aren't really interoperable. They're all really hard to use. Some of them you have to pay for and so on. And it's kind of a mess. In reality, in software code distribution, it's really, really nice. The whole package management and indexing of code is really good. So it would be useful to move over some of those solutions. And then there's, of course, problems of formatting. You have the data in some format, and moving it around between formats is a huge mess. And many times people spend a whole bunch of time just on this alone. Hundreds of hours moving data around between formats and making sure that it's right and so on. When in reality, you should just be able to use it. Then there's, of course, licensing. Many times you can't use the data that you found because it's not licensed correctly, and it has no license, and this is silly. And the last part is something that I kind of described as open access. There is a lot of open data out there that you can't actually use because it's difficult to get to, or you can't really fork, or you don't have the rights to republish. And so there's a separate part of this, which is making it extremely easy to move around the data and collaborate on it. And so in my perspective back then, I thought that, hey, data package managers would really solve this. If we take the source code package managers and create one for data, then we can solve a lot of these problems, right? So with distribution, we can use, instead of going from a centralized server-based type of thing, we could use peer-to-peer. And that is really good for bandwidth and really good for utilizing the network. For versioning, we can apply strict versioning semantics and make sure that people actually follow them, and require create a whole bunch of tools that really require versioning and so on. The same way that it works in software, to make sure that people are actually versioning their data and backing up every single version. So another part of this is, if you have a really large data set and you clean it up a little bit and you republish it again, you shouldn't have to republish terabytes of data. You should be able to just incrementally back up the next bits, but not have to duplicate all of the data from the past, right? And so this is doable if we have good versioning for large files, which, for example, Git doesn't do, but that we can do with IPFS. And then permanence is about a way of organizing a lot of people to share and distribute the same data. Indexing is, hey, we should just be able to have that where we can find an index of all the data out there. And so things like this, right? So there's a lot of ways in which software collaboration has improved in ways that data collaboration has not. And so back then, I started working on a thing called data and data DAGs. So data was like this package manager thing, and data DAGs was just this index. And yeah, like the goal was to just get it to be as easy as publishing code, but for data. And it was through that I discovered that there was kind of like a bigger underlying problem, because my solution there was to try to build something kind of like Git and kind of like BitTorrent. And I happened upon something larger, and this is how I came to create IPFS. And back then, actually, it was called GFS, and I ended up changing the name later. And so the goal when I shipped this was to, great, I'll ship this tool now, and then I'll just rebase it on top of GFS at the time, and so on. And so I built this like this package manager that you could use. And that ended up getting folded into the DAT project. I'm sure that you've seen, to some extent, the DAT project somewhere. I don't know how much you've looked at it, but I can direct you to, like, I can show you links to it and so on. But there we go. So yeah, like the DAT project is a project to create like versioning and data flow semantics around just like this distributed tooling. And I started on the data stuff, and then I kind of went down to a lower level to actually really think through how does data move around in the pipes, and to create like a good set of network protocols to move all this around. And then my friend Max, who was creating DAT at the time, focused more on the upper part of like the interfaces between people and being able to use it kind of like GitHub and so on. And we'll be collaborating on a number of things on the road. For example, data DAGs. We've been meaning to resurface data DAGs and actually have a nice index. But like now that we have IPFS as possible, we just need to like go and do it. So yeah, that's sort of the origin of IPFS, right? And so what happened was that I realized that the solution for this data problem, applied more generally, could be a solution for a number of problems in the web. And so this introduction kind of, I'll just make it a bit short. There's a few talks out there where I go in depth into kind of like the history of the internet a little bit, and discussing why the web has certain problems right now. So I'll just kind of mention them at the moment. But definitely I'll send you like links that you can check out where I kind of go in depth, right? So the web is this like really huge application platform that we all use, and that we rely on daily. We are now moving more and more of our lives directly through not just the internet, but specifically web applications, right? So these are applications that are delivered to us in our browsers, whether in a desktop or mobile, and which oftentimes run huge parts of our lives, right? Like from our work in terms of email to learning about new things in terms of Wikipedia and Khan Academy and Coursera and so on, to just entertainment, to like just any kinds of collaboration and so on, right? So it's the capabilities of the web and problems in the web directly translate to problems in our capabilities as humans today, which is kind of crazy, right? Like it's kind of crazy to think that just the fact that the web doesn't do certain things might mean a substantially different day-to-day life, which is kind of weird to think about, right? But yeah, so some of the problems that I'll just mention them, and we'll go extensively in detail here. But it's massively inefficient. Like data gets sent many times through the backbone. It is, oh yeah, and here we measured Gangnam Style, and apparently it's been served close to 500 petabytes of just Gangnam Style of the same video being sent out to 2 billion watchers. The web doesn't work offline, so if you get disconnected from the backbone, suddenly you stop being able to use your web applications, even though you may have everyone you want to collaborate with, you may be in the same room. It doesn't actually work that way, right? Like you still have to connect to the backbone, which is silly. It doesn't really work in mobile and IoT and so on. And of course, if there's any kind of like natural disaster or some major problem, the whole thing falls apart and nothing works, which is really crazy, right? Like when you think about the moments when you might need these applications the most, they're suddenly not available. And of course, there's like human disasters where there's things like censorship and so on, or people shutting down the internet. And then suddenly all the tools that people were using to communicate, like all these messengers, are suddenly not working anymore. And so this is a serious issue. And so I think we should be building web applications such that they work, or even applications in general, such that they work in these kinds of failure modes. And I use the term web application loosely here because a lot of these are mobile apps, but in reality they're connecting to each other and to the rest of the network through the web, and they're making web requests. So it's not a full-fledged web app, but it's still kind of using the same transport for the data. Then there's of course issues of data control. I think you know all of these really well, but basically like all these large companies start owning all the information that you give them, and any kind of reference that you have to the content that you might want to give to somebody else always goes strictly through them because of how HTTP works. If you make a post on Facebook or Twitter or something, you have to hand out a URL that goes through them. And that means that if you decide to like delete your account, or they go under, or they decide to change their policies or something, that data may no longer be there, which is not really good. And you can't really extract it and rehost it. Like you can sort of do it, but it's not the same thing. And certainly the links will change and so on. So ideally you would be able to create identifiers that don't change over time. Then there's tons of security problems. Won't go too into detail in there, except to maybe mention that the data is not authenticated or encrypted at rest, which means that there's all of these computers holding your data and other people's data. And yes, the connection between your browser and those computers is encrypted, but the data is not encrypted or signed, which means that anybody can change it or anybody can steal it at rest, which is a problem. And so we should be moving to a world where the data itself is armored. Cool. So lots of problems in the web, and turns out that with IPFS, with a small set of architectural changes in how web pages move around, we can solve a lot of these, or make a lot of these at least easier to solve in practice for developers. So things like making the web operate distributed so that you don't have a central point of failure, making the web operate offline or semi-disconnected, where you have sets of people in the same room and you should be able to get the data from them. Give permanence in terms of the identifiers and the data, such that if you have the data and you have an identifier for it, you can continue serving it over time, even though other people may you no longer have to rely on a specific website holding it, right? Like you can replicate all of your data and continue serving it. Making it safer, of course, cleaning up those interactions and making it more efficient and faster. So yeah, in short, the IPFS is just a protocol to upgrade how the web works. It is meant as a complement or replacement to HTTP, and that's kind of like the layer that we're going at. And you can think of it as a web of Merkle links. So I'll explain what those are in a moment. But it's if you've never heard of a Merkle tree or something, it's a data structure that also is used in Git for versioning, or in BitTorrent, or in Bitcoin for payments, and it's used in a lot of file systems and a lot of different cryptographic applications and so on. So it's definitely like a really great data structure that gives you a bunch of really nice properties. And IPFS is kind of a combination of these different techs, and we have this large stack of protocols that emerged around this. And so the gist of it is that you can think of it as a new network protocol where we have separated the concerns of different parts of the system, where we have connectivity between each peer and the routing for content as like different layers, and then we have how we represent the content as a kind of middle layer that we call that IPLD, and we have naming on top of that, and so on. This is again like pretty super specific, and I just kind of want to mention it a little bit and can dive into more detail later, or can send you to links. And so all the bottom layer, all of the probably the hardest part of implementing something like IPFS is getting the peer-to-peer stuff right. And all of that is we're creating a library called libp2p that people can use. And it's just like a lot of, it's a big library of like a collection of modules that people can use and import and so on. This is something that I wish people had done before and when they had built peer-to-peer systems like BitTorrent and so on, so we didn't have to rebuild everything. But from now on, people won't have to. Cool. So the most interesting part, perhaps, about IPFS is how to define the data. And so I mentioned this format that we have, IPLD. I'll go into a little bit more detail later about how it works. But the whole idea is that IPFS, in a way, is kind of like an internet of data, where you add different data structures into the system, and you're able to reference each other's data structures, but you don't really need to reference the locations. So when you think about Web 2.0, it kind of works like this, where you have servers connecting to each other, and these servers have databases, and you have both programs and data in each one of these locations. And these connections between servers will mediate interactions. And all you have really is references to servers. And so you have a reference to go and talk to a certain server and to run a certain program or to get some data. And what we're trying to move it towards is something more like this. And it's not just us. I think there's like the whole world of blockchains, and there's a really big push to invert the relationship here, where in reality you have you still have computers and databases and so on, but these are following standard open protocols that everyone can use. And it's really about the data and the programs operating together. So you hold references to data itself, not necessarily to specific servers. So that if I want to make use of some item in the web, I should be able to reference that item directly with a URI instead of a URL. So the point there is like it doesn't really matter. Like sometimes it matters who does something for you, but you don't ever want to depend on them forever. Like you want to make it so that you can change the dependency and use something else without having to change the references. So IPFS now is like this really large open source project. We have hundreds of contributors. Lots of people are working on it. There's like a substantially large network in terms of like the number of nodes. This still seems pretty small. This is a large map of like a heat map of like activity. This was, I think, like 2,000 nodes when this was measured, and that's about a fifth of the Bitcoin network. And of course, BitTorrent is much larger. These numbers will spike up once we deploy our browser version of IPFS, where it becomes extremely easy to like spin up new nodes. So these are 2,000 different developers and so on that are running nodes themselves. And I think not all 2,000, I think, or around at the same time here. These were measured over a period of, I think, a few days. So people definitely use it, go online, and disconnect over time. And we have hundreds of thousands of websites already on it, and hundreds of millions to billions of files. And people are using it for all sorts of stuff. So video distribution and streaming, so that works really well. So you can have video players that are loading video from each other's computers, and you never really have to touch any kind of central location. People are using it for legal documents, so there's a few archives of legal stuff. People are making entertainment sites like Imager. People are moving around 3D models. These are like really big, usually really big files and so on. So it's difficult for people to upload them, and so people are using IPFS for it. People are starting to design games on top of it. People are moving around lots of papers, both the actual PDFs, and people are using it for like blogs, personal websites, and so on. And probably the most interesting use case is totally distributed web apps. And this is where don't have to care about the text here, but the idea there is like that there's these websites where the code itself is stored within IPFS. And so when you access a site, you would download the code through IPFS, you run it locally, and you store all the data that you generate directly on IPFS. So there's really no centralized location, no origin server at all. And once you have that code and that application, nobody can really take it away from you, in a sense that can continue to work as long as you have the code. So the website can't, tomorrow disappear or something, or change itself. Like what happens often is that you find some application that works really well, you find a version that you like, but then a few days later somebody updates it and it's no longer exactly how you used it. And so this puts the control back out in the user's hand. And yeah, people are starting to make forums and chat and messaging and blogs and so on top of this. So there's like a couple of really cool applications. The chat one, I think, is the most impressive one, where you have like real-time chat over this. And that means you can do like end-to-end encryption there, and you can now really go, you can really have the security of the system. People use it for package managers, and I think this is where the best connection to data is, where in terms of like what I was talking about before, this data DEX thing, we'll be creating a data DEX again now that we have IPFS. And so the idea here is package managers usually are centralized, but with IPFS they can be completely distributed and peer-to-peer. So all of the data can be moved around computer to computer. And so if you need to download some code from each other, like, and you have it, and you know that that code is somewhere in the same room sometimes, you should be able to get it immediately. And we have it working with NPM already and Pacman from Arch Linux, and more are coming soon. People are using it for secure documents. So these are, think of like the distributed ledger use case. So everyone right now is getting really, really crazy about like using blockchains for storing signed documents and so on. And you don't really need a blockchain for that. You use a blockchain merely to timestamp, but the signed documents, people are actually storing them on IPFS. So there's a few sites that are theoretically storing stuff on blockchains, but the data is not on the blockchain. The data is on IPFS, and they just store the hash in the link to IPFS in the blockchain. And people are already using it at various places like this. So it's already in use in banks, legal archives, like blockchain people and smart contracts and so on. So this is, I think, probably one of the use cases that you care about. So yeah, like I mentioned, people are using it in blockchains for a lot of stuff. So Ethereum and Bitcoin communities both are looking at this. And lots of people are using it also to archive a lot of data. So there's several efforts to take data from all of these different sites and replicate it and archive it with IPFS. So that's really cool. And I think at least one university has, they dumped their entire archive, which was pretty exciting. And we're looking at things like Wikipedia and archive.org and OpenStreetMaps and so on, because those are usually, they have this huge bandwidth cost for them, and it really shouldn't be the case. Like once we have the browser implementation of IPFS, it'll be a lot faster. And so to explain a little bit of how that works, which I think the most important thing to think about is how does IPFS actually work, where you have a link and you try to retrieve the data, right? So normally you're used to an HTTP link like this, where you have a domain and a file, and you are mapping it to a location, right? So what that looks like is this, where you have say that you have the internet and you have a whole bunch of computers there, and maybe all of them have this specific file, but only you must go access it from one specific host, because that's what the IP address tells you to do. And instead, what if we could use hashes and then just try and find who has the data? So you could do something like this, where in reality, anybody could serve you the data, even if they're next to you. And so we do that with Merkle linking. And so this is where we use the hash and the content address of something, and we create this graph underneath the hood. And then we point key links to those. So these are I can go and explain this towards the end, but this is where we have signed links that don't change, but the data is mutable. So the content addresses are immutable, and the content for those can never change. Once you do it, if you change the file or something, the address will change as well. The key names are the ones that you can hand out the address, and the address is the same, but you can update what they point to. So the key names are pointers to immutable data, if that makes sense. You can think of them kind of like branches in Git. I can explain how that works exactly later on. But then the last part is you can actually use DNS to achieve human readability. So at the very, very end, you can use DNS with like a human readable name, and you map it to a key name, and then you map a key name to a content address. So you have human readability pointing to just mutability, and then mutability pointing to immutability. Hope that just, I guess I'll ask right now, like, are there any questions around this? I can explain how the key name works, but does that sort of make sense?
Yeah.
Yes.
Cool. So the model for IPFS is that IPFS is a protocol, and it's a program and a set of tools that people run, and this can be, and so any computer or whenever there's a running program that implements a protocol, that's called an IPFS node. Each one of these has a public-private key pair. These nodes connect to each other and find each other through a series of discovery protocols, and then they store and distribute part of this huge DAG of content, right? So like there's this really, really large graph of content, all of which is linked through usually Merkle links that are immutable, but sometimes you have mutable links in there, and you move around those pieces of content, and that is like what IPFS is for. And you can use it for you can run it as a server, or you can use it embedded in applications. And we're kind of destroying the distinction between a client and a server. We want everything to be IPFS nodes. And so you should have, when you have an application, you should be able to run it usually kind of like all client side. Though there are, of course, like processing that you need to do sometimes in the internet, but you shouldn't depend on that to be around as the sole arbiter of truth. Like you should be able to just use those, but not necessarily depend on them to remain there in the future. All right, so I'll jump to like open data use cases directly, and then we can go into like the more in-depth technical details. So this just kind of maps back to what we were discussing earlier. So the efficient distribution of large data, like this really just means when you're in a room with a lot of people, you should be able to move data as efficiently as possible. And this applies the same way to data centers, right? So if in a data center, one computer is very close to another, you should be able to just short circuit through the internet and not have to go through some like third parties elsewhere. So versioning larger complex data, this is straight up the same kind of semantics that Git gives you, but applying it to large data. And so this is something that we're achieving with different kinds of data structures. So we have a commit kind of like Gits, and so you can commit on data. This is not yet shipped in the main distribution, but it will be relatively soon. We're just perfecting the formats right now. But the idea there is like you should be able to fork data and to create patches and so on the same way that you do so for code, and you want to be pretty efficient as to how you do that. I think one of the main issue with most versioning systems today is that they don't work on large data. And there are more interesting data structures there that people are using. These have less applications to data and more to distributed applications, so CRDTs and so on. There are like different distributed system style algorithms and so on that you can use to have version data and so on that converges over time. But that's, I guess, like less interesting to just data archives. Then there's the whole notion of signing and authenticating data. So this is what we were talking about before. So like you should be able to just take documents, sign them, and just put them in the network. And if people can verify that the key is correct and that the signature is correct, then they have a much stronger belief about the authenticity of the document. And this is not really done on the web that much these days. Of course, like code is signed and a few different groups actually sign their data, but on the whole, like the web is usually completely unsigned. And so that's something that we can help a lot with. Yeah, so data permanence, like remove this notion of like landing on 404s. Like if the data was there at some point and somebody has it, you should be able to serve it, right? So many times these 404s are merely a result of people sometimes changing their URL scheme, so they move around files in their server, or maybe they stop hosting it, but other people are hosting it. So you shouldn't lose that just because one person stopped doing so. And so yeah, this goes back to this. Like you should be able to, if you have a key name, anybody should be able to serve that. So yeah, so then data archiving and mirroring. So the archiving part is really important to us. This is where, for a long time, just we have this really huge imperative to archive the data that we use for all sorts of important records. And as we've moved to the digital age, that hasn't really kept up the same way. So lots of digital archives are really fragile and could disappear. Many times the data is hosted only in a few data centers, and it could be victim to some larger scale problem, but it isn't as replicated as it should be, right? So you would think that going from paper to bits, you would get many, many more copies, and you would have a much more resilient system. But in reality, it's kind of not that way because we haven't made it so. Like it's actually pretty fragile. And there's a lot of people really worried about this, including the people at the Internet Archive who've been trying to replicate all of the web itself and back it up for us. But they can't do everything, and they certainly don't have huge data sets like the petabyte-sized data sets and so on. They don't back up those, and that's where a lot of the scientific data is stored in things like that, and it could disappear. There's already been a few cases where some archives got lost, and so that should not happen again. So yeah, we should not have another like burning of the Library of Alexandria moment where suddenly all our papers are gone. That would really suck. And so accidents do happen. Data centers do catch on fire. Digital media does disappear. So we need to prevent that. And the way we can do that is by creating these like indexes of all of the data and helping people replicate and distribute and mirror the data. So this is stuff that we don't have fully built out yet, but we have spec'd out and we'll be working on this year. These are creating tools that can identify how many other people have a certain piece of data and making sure that there's always a certain number of online replicas for something, right? So you would be able to join a group in a sense that will collaboratively back up some archive, and you'll be able to allocate some certain amount of space to that group. And so the group should intelligently redistribute the data depending on what nodes are online right now, right? So if a whole set of nodes disappears and suddenly you have an uneven distribution, you should be able to remix who has what to achieve like a more uniform distribution so that you increase the chances of everything surviving. And yeah, so and we'll be working on the dataset index stuff because I think that will be pretty interesting for people. So this goes with CCAN, right? So and you're familiar with CCAN. So when I wrote that talk and so on, I wasn't that familiar with CCAN. And one of the things to do is potentially like upgrade how CCAN works to use these kinds of systems where it's no longer like an individual portal that has to hold all the data, but instead is just the index portion and is pointing to IPFS URLs or URIs that anybody can distribute. And of course, there's like the disconnected offline use. Sometimes when you think about like a crisis situations, right? So this is like a picture of it's part of the refugee crisis. I think this was Pakistan maybe, and these are people signing up refugees as they're coming into the country. And so those laptops there where they're like taking information, those are probably connected to the internet. It's not clear. If they are, they should be able to like look people up. But if the connection goes down, then that whole station is useless, right? And so there's this brittleness to connectivity today where people can easily lose connectivity, or the connectivity may not be that good, and then applications stop working simply because most people are designing applications to work in the best case of like really nice fast bandwidth. They don't really deal with a case of poor quality bandwidth and so on. Of course there are exceptions, but the majority of web applications don't work that way. And so the goal is to build the tooling and infrastructure underneath the hood so that developers don't have to think about it that much. They just have to write their application, and the system can move the data where it needs to be, and you can create like replicates of large amount of the data, so you can continue operating offline or continue to getting data in sync when the network comes back online. And I think like perhaps like the last thing to mention is like access controls with capabilities. So this means maybe sometimes you want to do like selective disclosure or something, where you want to reveal certain pieces of information, but not everything. So sometimes this is talked about as like the bouncer problem, where somebody goes to a club and they want to verify that only that they're over 18, and they really don't need to reveal their entire like license that includes their exact birth date and their address and everything. In reality, you should be able to just have signed statements that prove that you are that prove certain things, and you'll be able to like selectively disclose those. This also has a bearing in health data, right? So this is where the hospital data stuff comes in, where maybe you want to be able to disclose certain pieces of information, but not everything, to specific groups over time, and that should be doable. And we can do that with capabilities. So this is not live and working today on IPFS. You can do it if you know how to use capabilities and so on. You can do it certainly, but we want to have a library available so that so it's very easy for people to do this, where they just have to like follow like a tutorial basically, and then suddenly they have like a selective disclosure document that they can reveal over time. Cool. So now this is where I like pause because I've just been talking for a long time, and I have like this other set of slides with like kind of like a lot of details about how different pieces work. So all the IPLD stuff, how the signed links work, how IPNS works, how the versioning is going to work, and so on. And I can dive into that, but I also want to not just talk endlessly at you. So if you have any thoughts or questions now, we can discuss those. Or how are you feeling?
Overwhelmed with all information and excited at the same time.
Yeah, I bet. Probably not the best bar moment talk. I should have thought that through more.
No, like, you are very good. And like my question would be, and I will constantly ask when I'm talking to IPFS, is it possible to delete data from IPFS?
So sort of. To delete data from IPFS means to not have people who are hosting it, right? And so that actually is the same way that it works today in the web. So if you upload an image, say, right, and you have it in a website, and you want to delete it, then you can take it down, and so that URL no longer works. But usually other people may have replicated that information by that point, and so you can't really take it back, right? So the internet, or rather information, works in such a way that once you've revealed information, it's very difficult to take it back. And so as long as there's somebody out there that wants to host it, they can continue to do so, right? So, and this has happened a number of times with all sorts of content yeah, like if it's out there, it's out there. And so IPFS doesn't fundamentally change that. It just makes it so that, like, that already happens in the worst case, right? So in the worst cases of like the data that most people really don't want online, some group is like always making available online. So in the worst cases, it's already there. The case where it goes bad is when you have these like large data sets or something that suddenly disappear, and somebody has them on the network and would be willing to serve them, but you don't know who it is, and you can't find them. And like that is like an annoying problem that shouldn't be there, right? And so today, when you create an application, even if you use linked data, and even if you use nice URLs and so on, you're still dependent on the continued existence of that organization. If that organization disappears, 5 years down the road, that data is going to disappear. And so you're really like building on unstable foundations, right? Like you're building on mud in a way, because that can disappear at any moment in time. And even large companies will go and like change their products and make them disappear, right? So things like Google Reader disappeared. Large sites go under every once in a while. And so we want to live in a web where once you have a piece of data, you should be able to build on that piece of data, as long as you replicate it, right? So the content model is that the content isn't immediately spread to people. So like this is, I guess, like other peer-to-peer systems work such that you add a file and then immediately that file gets distributed to a lot of other people. That's not the way that IPFS works. So with IPFS, you only download the stuff that you are willing to download, like explicitly. And this is an important distinction because it has like a lot of like legal complications, right? So like the other peer-to-peer systems have legal problems because if somebody uploads something that's really bad, like illegal bets, suddenly they get distributed to a whole bunch of other people. So that means that nobody wants to use those peer-to-peer systems for legitimate traffic because you might be stuck hosting something bad, right? And like you don't want to do that. And so with IPFS, that doesn't work that way. What you do is you add the content, and so you make it available on the network. And it's not until somebody else pulls it and replicates it that it actually moves. And so what that means is that if you want to make sure that something is available and live, you have to make sure that that will continue being the case. But that means that you have the option to do so, right? So the URL, you can do so without the URI is changing. And that's like one of the important details here, where you can band together with groups and say, great, like we care about this data continuing to exist. Everyone allocates some amount of space, or they hire it from a cloud provider or something, and you store the data there. But any one of those individual organizations can disappear over time, and all of the URIs will continue to work just fine. You can change providers, you can change locations, you can change everything about it. As long as you're still connected to the network providing it, then you're good. And so like that's where the added resiliency comes in. Now, we are working on a network called Filecoin, and this will come on top, where it is more like the traditional peer-to-peer systems where when you add data, other people retrieve it from you, and like you come at it together. But what that is doing is really like it's a different nature. It's like a service provider. Think of it a little bit like AWS, where you have a network, and then you sort of hire the network to back up your data for you, and you either pay the network in space, as in like you donate disk space to the network, or you pay it in money, like you get some cryptocurrency and you spend it there. But that's like different, and that's gonna be layered on top of IPFS. Cool. Does that sort of make sense?
Yes, it does.
Cool. Other questions?
You just like to see some examples, just some real. Can you just show some real examples? I think that would be good.
Yeah.
Please.
Yeah, absolutely. So, yeah, let's see. So I don't know if you can see that. I'll increase the font size. Cool. Can you see that? Or should the font size be larger?
We can just see you. We don't see your screen.
Oh, I see. I need to share the screen. That's cool. So right now, IPFS works through mostly a command line environment, in that we just haven't made it all the way up to the top tools where you'll be able to just add and so on everything through a web interface. So, oh yeah, so what you were mentioning before in terms of like a folder that you add and so on. So today you can get it with Fuse, so you can actually mount IPFS like a file system. And so it works a little bit like a Dropbox folder. It's not great yet, and it works on top of Fuse, which isn't super effective, but I can like sort of demo it here if it'll work. Mounting. I think I like broke my Fuse distribution right now. So let's see. Will this work? There we go. So now I can go into like a folder like here. I can have a folder, so I can like see into foo, and like I can open foo. Let's see. Does this work? so I can like move a content in here from like say that, and so what that is doing, it's treating it a little bit like a kind of like a Dropbox mount, and so I can like view content from there, and I can actually fun bugs. Yeah, I think I totally destroyed my Fuse installation. One sec. This is one of the reasons we don't directly advertise this one thing that much, because it's a little bit flaky still, and people have like varying degrees of like success. But people are already working on like nice tools that are like drag and drop, where you have, and so this sort of works on the web UI already, where people you can drag and drop into the web UI, kind of like a folder. But this will look a lot more like the traditional Dropbox thing that you're familiar with, and so on. But yeah, so like here I could like drag and drop a file, so I can go from like yeah, like I can let's see, sorry, random stuff. And like just drag and drop a file and like just add it there, and so like that adds it, and so like now it's added. Is this okay? All right, I'm running dev builds of stuff, so I'm usually like on. That's why it says like, hey, new version, because I have like actually like a different version that's the one distributed. But yeah, so you can add content this way, and so like now, great. So like now that's added, and so you can like view it directly. So that just added here, so I should be able to like just view it, and so I now have it on the web and available. And so this URL I can exchange this for, you know, like the global gateway, and I should be able to like download and view that, right? And so like here it's pulling it from my computer, and so this is going through this one link is going through the global gateway. So this is like a set of servers out there that found the content from my computer, pulled it out, and so now I can now refresh this page, and this will go much faster because now those computers have it. This one didn't go so fast. So it depends on like the what the connection is doing and so on. But now those sets of gateways will now have that file that I just added locally. And so yeah, I can show you also like I mean, you saw the CSV files that you already had and so on, right? So this is where I put them, but yeah, so like you can easily add a whole bunch of files and have like a directory listing, right? So like our entire distribution of IPFS. So like we have this site now that shows you like the different binaries that you can download and so on, and this whole thing is hosted with IPFS, so that I can view it like locally if I wanted to, right? So I can go to localhost 8080 IPNS, and this should download the content as well. I'm not on a super fast connection right now, so it might be a little bit flaky, but great. So this time that the site rendered, this is being pulled directly from my local machine. So the content is here now. So I could disconnect, and I could like continue viewing the site. And so you can get like standard directory listings, like where you can actually go into like, you know, you can add data this way and get like a similar archive to most other things, where you can like have entire directories and directory structures, and these could be you know, any kind of archives, right? And so other people can help you distribute the same content here and help host the data, but you still see it the same way that people are used to on the web. Now for I wish I had like a nice demo right now of like being able to drag and drop stuff, but like it is being worked on. So let's see if I can just like show you the repository. I think it's like file. I'm like trying to find it. There's a number of people that have been trying to attack that. So what's this? Oh, there's no screenshots. But yeah, so there's this like file browser thing that is kind of like it looks like a folder, like a regular folder in your UI, and you'd be like dragging and dropping things the same way, and it adds it to IPFS each time. And when you add something, it's deduplicated, right? So if you add a large file that has large blocks that are the same, it'll usually find those and deduplicate them. And this web UI that I showed you, so this thing, this application, so this is a web app itself, right? That has like, it's just a website like any other, right? But what's going on is that this is actually like entirely hosted through IPFS itself. So these are real peers that I'm connected to. So you can see, it's like finding them. It's doing for each one of these, is doing queries to an index of IP addresses to find out where they are. So this is like populating the network with like where they are. And these are people that I'm like directly connected to. So I'm directly connected to 90 or so peers. And this whole web application or whatever is hosted and distributed through IPFS. So this is what we meant, like a totally distributed app. And so I'll try to like demo the chat. So there's a chat that like works. Hopefully this will work. This is developed by somebody else, not us. But this is like a chat system that you log in, and you can then start like chatting with people. And hopefully it'll load. At some point we'll make something like this ourselves that we can use and like it's reliable and so on. But demo time, let's see. I know like he runs like some system that helps make it run. So I don't know if he's like maintaining it at the moment. Yeah, it's not online at the moment. That's annoying. But I can show you a link at some point to this, and you can like try it out. But oh, that might be why it's not connected. Cool. No, it's still connecting. Yeah, for whatever reason, like this thing is not working at the moment. But this person built this whole chat thing, and there's a repository for it, and like here it's kind of like what it looks like. So it like works a little bit like this, where people like start entering messages, and it's meant to work a little bit like IRC. And right now it's a little bit painful to like set it up and so on, but that's getting easier and easier over time. Like this is pretty new. Like he developed it pretty recently. So there's a lot of activity right now happening with like all of these different kinds of applications. Here's another interesting one. Is like the data set package manager type of thing. So registry mirror is another one of these things. Let's see, where's the blog post? This is the watch one use a computer version of the talk. Yeah, so yeah, David wrote this whole tooling around NPM so that when you use NPM, it actually pulls out the modules all from IPFS directly. And like that works really, really well. And a whole bunch of people are like using it already. And he has like this video demo that goes through it and how it works and so on. So I'll drop a link there. Yeah, and I think, oh yeah, the archives. So this might be interesting to show you. So we have this whole effort around replicating large archives of data. And so there's a whole bunch of them that are already going, like for example, like, yeah, so like archive itself, Project Gutenberg, Y archive, entire snapshots of like different, protein data bank and so on, Stack Exchange and so on, and like all of these usually will have like some URL of like progress of like people that are like starting to make those archives work. Trying to see if I can find. Oh yeah, I guess if I do. Yeah, if I usually Google will show me a few. Let's see. Yeah, here I'll be able to like jump directly into like a lot of the archive pages in a moment. Oh no. Where did I have that? Yeah, so there's like these whole set of maybe it's here. It's like yeah, here we go. So here, for example, right? So this is a PDF that is coming from the archive.org website. So this is like a paper, but it's not actually hosted from them. It's like hosted through IPFS. And so here you can like see like the rest of the contents of the archive. So here's like a whole bunch of papers and PDFs and so on. Sometimes they come along with data, and like you can see like lots of this stuff. And so you can replicate this entire thing yourself. And so these are we were right now only able to replicate the ones that are all CC BY, because there's archive has like different licenses for the data. So some of them we can't replicate. But like this is like an archive of all of the PDFs of the stuff. So like I'm viewing these papers, and they're not coming from the central server at all. They're coming from different peers that have them. And so this all of the PDF right now is being loaded from different sets of people, right? And this right now I'm loading it through the global gateway. I can load it locally, and this might go a little bit slow because it has to pull a bunch of stuff. Oh yeah, I broke it. Let's see. Right. Great. There's also like querying multiple different hops. So let's see if it'll work. Great. Yeah. So this now I'm viewing this archive now from my local machine. And yeah, it's a little slow because there's I guess not that many computers replicating this archive at the moment. And my connection is slower. So if we view it through the global gateway, it's better. I can send you a link to this so that you can like play around with it.
That would be great.
Yeah, so let's see. I'll put it in. Yeah. Yeah, you should be able to just click on that, and you get like this large archive of stuff. And you can like dive into it and see the PDFs and so on.
Can you just show us the digital signature? I'm interested in that. Just show us an example. Picking a file, what happens, or
Yeah. So yeah. Let me show you. So let's see. There's two things around this. One part of it is creating a signed link, and the other part is actually just storing signed data, right? So the storing signed data, that just means take a document and sign it through any kind of algorithm that you want. And then that way you just move around the content along with the signature, right? So this just means like traditional PGP style stuff, right? So like I forget what the actual commands with GPT are, but like you can use GPG to sign a set of data, and then like actually like include like some file there, right? So I'll just like look at Stack Overflow and see the exact commands. GPG sign. Google wants me to confirm that I'm a human. I've been searching too much. let's see. Sign. And we have like we're making our own signing tools and so on that are a lot easier to use, just because like GPG is not the same. Oh, maybe Keybase will do it. So let's see. Sign. Generate for me. In fact, let's think. Let's see. I have Keybase locally. Keybase is like much easier to use than GPG. So Keybase, sign. This should work. I forget the exact documents. What you end up with is a file that just has the actual signature, and that gets added along with the rest of the file. So then you have it there and you can verify it. So it's like the less interesting case for us. It's just kind of like, great, you have a signature along with it. What I'll do is I'll actually like show you a direct example. Like I'll write out an example of how to do it, and I'll send it to you. But like the more interesting part is when you have a signed link. And what this means is like you have an actual URI to something, and that's using a public key, right? So this is, I'll I guess explain how that works, and then I'll just demo it for you. So this goes into this stuff. 1 sec. Yeah, so we call these like Maziris links because they were kind of invented by a guy named David Maziris. So the idea is like this blue part is a hash, but it's not the hash of the content, it's the hash of a public key. And what that means is that you can, if you have a public-private key pair, you can create a link to some content that you can update over time, right? So you can point it to this, to one version of the content now and point it to another version tomorrow and so on. And the way you do that is by creating a pointer that's saying, hey, like the latest version of this link is this one, and you sign it with a private key. And so you can follow that link, right? So having the hash of the public key allows you to search on a DHT for these records, for the latest version of the record of this pointer, and you retrieve it, and then you can follow it to the content. And so that's kind of like in theory, sort of how it works. And we treat it as like key addressing, and that's what we call it. Like we call it IPNS key addressing. And the record's a little bit more complicated. I don't necessarily need to go into detail there, but like the idea is that it has like the record has like the actual value that you're pointing to. It links to the key that you are using to sign it, and it has like the actual signature. And I'll just demo it working for you. So right now we have it under IPFS name, and right now you only have one name, but this will be, you'll be able to generate as many links as you want pretty shortly. So say that right now so say that I add some content, right? So IPFS add, I added like some content, right? And I can look at that set of files here. So I can go to like localhost 8080/IPFS/ the actual hash. And I have like the actual content that I just added, right? So this is again like that picture, and I have some other stuff like picture of a cat and some test files. Great. So if this hash will change if I change the contents of that directory, right? So if I add another file like this, and I add it again, then the hash of the directory has now changed, right? So now it's something different. And I can go, I'll open it in a different tab so you can see the difference, right? So now it's Q May something, make that larger. So this thing here is now different because it has this another file thing that I just created. So now the top hash is different, right? So this is kind of what you were seeing before. The rest of the hashes are the same because that content hasn't changed, and all of that is deduplicated. So that's one of the things here. Like none of this content is stored twice; it's only stored once. But you still have changed the root of the thing, so it is affected, right? So the way we fix that is by using names, and so I can just do IPFS name publish and pass in that hash as an argument. And what this is doing is it crafts that record and publishes it to the DHT. So my name is this one. So I took this hash, this QMQ7 whatever, and published it at this other value. And we'll make a lot of this easier to use. Right now it's a little clunky, but that means that I can now go to localhost/IPNS and access that link. Let's see, I think this time. So right now it's like trying to query the DHT to see if there's another record, and sometimes it takes a bit. This is part of the reason we haven't like pushed this one very hard. So yeah, so this is like the old version, right? So this it's a different hash now, and it's pointing to the old version. But now I can take the new version, like the new version of the hash, and publish that one. And so this is going to do that same thing. It's just going to update the pointer. So great. So now I publish the same name to the new version. So that means that I can refresh this one, and it will. I'll look at it on a global. Right now, it's like hitting some cache. Let's see. Will it work? Oh, that might not work because. Let's see. Great. So this, I decided on like the global gateway, and like this is like the new updated version of it. So it has the another file thing, but the URI, the URI remained the same. And this is not human readable, right? But what it gives you is like it gives you the ability to like update the pointers without relying on any kind of centralized authority. You can use human readable names, and this is the other layer of using DNS linking for human friendly names. So this is like this part where you go into like actually nice links, and this is how we. So that site that I showed you earlier, that dist IPFS.io, this is how we do that. So what this is doing, this website is actually going to IPFS.io/IPNS/that link. And what this is doing under the hood is it's taking that domain name and looking for it on DNS, and it finds a. So if you look for a text record, it finds this text record here. And so this is pointing to the latest version of the content that you want. And so if I wanted to update this site, I just update that DNS pointer, and that's it. And so that URL remains the same. And it's also human readable, right? So it's something that you can give people a site that looks exactly the same as sites look today, right? Like this.ipfs.io does not look like, different at all. It's like looks exactly the same as people normally see it. But this right now is getting hosted by IPFS. So this will go to the global gateway that we have right now. But if you have like a local installation in your browser, then it'll pull it from your local gateway. Does that kind of make sense? There's a lot going on in making that work, so it can sound pretty confusing, but like the result is really nice. Like you get something that doesn't look at all different from what people are used to today.
So just to summarize, if I have a folder and has 5 files in it, that's grand. If I give the link to the individual files to people, that's perfect. But then if I add a 6th file, all that's going to change is the link to the folder itself, and the link, obviously, to be a new link to the 6th file. Yeah, no,
right. So yeah, that's the adding part where we added different directories here. So that's like the part where we had the, like in fact, like I'll just do it like slower this time. So let's say that we have like 5 different files, like 3 different files. We have a directory with 3 files, 1, 2, 3, cat 1, cat 2, I guess. So I have like 3 different files. They each have a different number inside of them. And if I IPFS add that directory, then yeah, I end up with some set of hashes and a different one for the root, right? And this is kind of like what we were seeing before. And so yeah, I can see those files and so on now on the web. It's just like the number 1 and so on. But the hash of the root will change if I add a 4th one, right? So if I go now echo and add a fourth, and that does change when I add it. But the only thing that changes is the last one, right? So the first three, like notice that these three hashes are the same there as they are here, because it's the same content that is getting duplicated. It's just the root has now changed. But this is what the names are for. The names allow you to hand out the same link without having to change the link.
Okay, that's good. That's good. That was a question.
But
Cool.
if I use the old hash, the old status, isn't it?
Sorry, one more time?
If I use the old hash with only 3 files in it, I still get the status of 3 files.
Yep. Yeah. So all of that is immutable and hosted there. You can think of it like Git and version history. So it's all there. And so the name, the one that's mutable and you can move around, that one is just a pointer to the other ones, right? So you have all this immutable content that's being added, and you're just pointing to it. It's really a graph, right? So I can show you like what is actually happening underneath the hood. So so we have this tool called GraphMD that actually visualizes. Actually, I'll do it for a larger directory. This is just like I'm gonna create an SVG of the graph, right? So this is like a directory that I was adding. It has a whole bunch of stuff, and like here's that directory that I was doing like with 4 files named 1, 2, 3, 4. So here it is. Here's that directory, and here's the content, right? It's just like a graph underneath the hood, and here's like a whole bunch of other stuff. Here's like the tree picture. It got chunked. So this is one file, but it got chunked into multiple different subchunks because it's pretty big. And there's a whole bunch of other stuff. So here, there's like a big archive with a lot of data. So this, if we then go and create a new, say that like I just like replicate the entire. So say like I'm just gonna create a copy of the entire directory and just call it basic2. And then I'm going to add both of them to, I'm going to move like basic2 into basic1. So I'm just like creating a whole bunch of duplicate data right now. And I'll show you like what happens. It's the same thing that happens when these files are added. So being able to like visualize the graphs actually like helps a lot. So now with all this duplicated data, what happened is that the graph now has a whole bunch of different names for the same stuff, right? So you have the root directory, you have these 2 files, and all of these and files and so on are being pointed to by 2 different things because they're referenced in 2 different places. Does that make sense? I don't know if I went too fast on that.
Yeah, no, that's
so it's just
fine.
Yeah, so it's like deduplicating everything. So all of the names remain the same.
So yeah, look, it was so much great, and yeah, you're showing magic. It looks so easy, so simple.
It's simple. It's just a lot of it right now. We're making nicer and nicer front end tools for people to like use without having to like know all the command line stuff. But we're not fully there yet with some of them. And yeah, we're making like tutorials and guides. It's just maybe something that would be helpful to, because the community kind of makes stuff as it's requested. If you send like a list of things that you would love to know how to do, then we can start creating guides for doing all of those things. Because we just need to improve our docs. Like our documentation is pretty sparse right now, and we know that, and we've been allocating time to do it and fix it in February and March. So we can go and do that.
Look, thank you very much for your time, and yeah.
Yeah, thank you for having me. Sorry if it was a little bit too diving too much into the tech right now. I know it's like late over there.
Fine.
Okay.
Yeah.
Thank you so much. Thank you so much.
That was great.
Yeah, absolutely. Thank you. Cool. All right.
We'll
Take care.
see you online.
Yep, sounds good.
We'll be in touch with the list of asking for help.
Sounds good.
So, thank you. So.